Let's start with some important terms with optical isomerism. Like the first is optically active and optically inactive compound. Now, what is an optically active compound? Which rotates the plane polarized light. What is an optically inactive compound? Doesn't have any effect on plane polarized light. Optically active compounds can be of two types. They may be dextrorotatory. They may be levorotatory, which rotates the plane polarized light towards right or clockwise are called as dextrorotatory, represented with a plus sign or with a small letter D, which rotates the plane polarized light towards left or anti-clockwise, generally represented with a negative sign or small letter L. Now, the optical activity of a compound is decided with the three factors. Now, what are these three factors? One is presence of an unsymmetrical carbon. Presence of an asymmetric carbon, or this asymmetric carbon is also called as stereocenter. Now, what is asymmetric carbon? Carbon bonded with four different groups is called as a asymmetric carbon, or that is called as stereocenter. Now, the second condition is the compound should have non-superimposable mirror image. Non-superimposable mirror image. What does it mean? The compound should have a mirror image which, after rotating at 180 degree, should not be superimposed on the original compound. Like, say if I have a compound like this, C, here is P, here is Q, then R and S. Now, if we see its mirror image will be like this: C, P, Q, R, S. Now we rotated this entire thing at 180 degree. Then the mirror image will become like this. R, Q, S, like this. So this is 1, this is 2, this is 3. Now, in the original compound, Q is towards the observer, while if we talk about the mirror image of it, then Q is away from the observer. So the two, that is 1 and 3, 1 is the original compound and 3 is the mirror image after rotating at 180 degree. So the two are non-superimposable on each other. That is why such a compound will be optically inactive. And the carbon present here is called as asymmetric carbon. We represent it by putting an asterisk mark on it. So this is asymmetric symmetric carbon, or this is called as stereo center. And the compound which are possessing the non-superimposable, this type of compounds are called as chiral compounds. This type of compounds are called as chiral compounds. But if the four groups are not different, if the groups are same, any two groups are same, then too the compound will not be having a non-superimposable mirror image, and that type of compounds which do not have non-superimposable mirror image will be optically inactive, as well as the compound will be called as a chiral carbon, and the carbon present in this compound is called as symmetric carbon, right? So say for example we have a compound that is, say it is propane 2-ol. Here is OH, here is CH3, CH3H. So this type of compound we have. Now if we see its mirror image, then mirror image of the compound will be like this: COH, CH3, CH3H. So this will be the mirror image, and if we rotate it at 180 degree, then the mirror image will be like this: OH here, and then CH3, CH3H. So here we can well compare that 1 and 3 are superimposable. The 2 are superimposable. Why the 2 are superimposable? Because the carbon is symmetric. Because carbon is symmetric. Symmetric carbon means which is not attached with 4 different groups. The carbon is symmetric, and the compound is called as optically inactive and is a chiral. Compound is a chiral compound. So that is how we can talk about the optical activity and optical inactivity. Now sometimes it may happen that the compound has the asymmetric carbon, but still it is optically inactive, and the example is Mesotartaric acid. In case of Mesotartaric acid, the compound has 2 chiral carbon, but still the compound is optically inactive. Now what is that example? That is, say for example we have COOH here, H here, OH here, CH here, OH here, COOH. Now here if we see that carbon 2 and 3 both are chiral carbon, both are asymmetric carbon, but still the compound is optically inactive. Why the compound is optically inactive even after the presence of 2 chiral carbons? That is because of the presence of element of symmetry. So the third condition which is to be followed, that is no element of symmetry. It has to be no element of symmetry. There should not be any element of symmetry, means there should not be any plane of symmetry, any axis of symmetry, nothing. So no element of symmetry. If it has an element of symmetry, then the compound can be divided in 2 equal halves, and the rotation caused by one half will be cancelled by other half. So if the first half is dextrorotatory, assume that if say the above one is dextrorotatory, then lower one is levorotatory. So the dextrorotation caused by this will be cancelled by the other half. So that is how the overall compound is going to be optically inactive, and this phenomenon which is making it optically inactive is called as internal compensation. Now what is this internal compensation? Internal compensation is the compensation of the optical rotation caused by one half cancelled by the other half. So that is called as internal compensation, and this type of compounds which are having 2 chiral centers or which are having 2 stereo centers but still optically inactive because of the presence of an element of symmetry are called as meso compounds. So here this is tartaric acid, and because it is having 2 chiral carbon and plane of symmetry. That is why it is going to be optically inactive, and this type of compound are called as meso compounds. So this is a mesotartaric acid. We may have another example of this type of compound. Say if we have 2,3-dibromobutane. 2,3-dibromobutane. This is the compound 2,3-dibromobutane. So if we talk about this compound, here again we have two chiral centers, but still the compound is optically inactive. Why the compound is optically inactive? That is because of the presence of plane of symmetry, and because of this plane of symmetry, the compound can be divided in two equal halves. So it is symmetrical compound, and that is why it will be optically inactive. And the phenomenon taking place here is internal compensation, and this form is called as meso form. So meso 2,3-dibromobutane. Now let's do if the arrangement of atoms is not like this. If the arrangement of atoms is like this, say the arrangement of atoms is like this. Now this is tartaric acid, and this is the optically active form. This is the optically active form. Say this is D form, D or dextrorotatory. Now its mirror image will definitely be levorotatory. So the two are called as enantiomers. The two are called as enantiomers. The mirror image will be like this. The two are non-superimposable mirror image. If one is dextrorotatory, then another is levorotatory, and the two are non-superimposable mirror image of each other. Non-superimposable mirror image of each other, and called as enantiomers. While the if we number the compound, say this is 1, mesotartaric acid is numbered as 1, this is number 2, and this is number 3. So if we compare 1 and 2 or 1 and 3, 1 and 2 or 1 and 3 are the same compound, that is tartaric acid, but one is the meso form optically inactive, while 2 or 3 are the optically active form of tartaric acid, and this kind of compounds are called as diastereomers. Now what are diastereomers? What are enantiomers? Enantiomers are the non-superimposable mirror image of a compound. One of them is dextrorotatory and the other will be levorotatory. Now what are diastereomers? Diastereomers are not the optical isomers of each other. Here we should see that this one compound 1, that is mesotartaric acid, this is optically inactive, while 2 and 3 are optically active. So if we talk about 1 and 2 or 1 and 3, they are not the optical isomers of each other. They are the same compound, same structure, but they are not having any mirror image relation of with each other. Not superimposable, not non-superimposable, nothing, no kind of this relation they have of the mirror image relation. So this type of compounds are called as diastereomers. So diastereomers are not the optical isomers. They don't have any mirror image relation also. They are called as diastereomers. Now moving to the next term, that is Rasmic mixture. Now what is Rasmic mixture? If the D form of a compound is mixed with L form of the compound in equal quantities, then the compound will become optically inactive, and that is called as Rasmic mixture. So what is Rasmic mixture? Rasmic mixture is optically inactive form. So any compound which is optically inactive because of the presence of two enantiomers in equal quantities, Because two enantiomers are in equal quantities, one will rotate the plane polarized light towards right while the other will rotate the plane polarized light towards left. So overall mixture will become optically inactive. Why? Because the compound is having the non-superimposable mirror image, right? The compound will be optically inactive because of the presence of two enantiomers in equal quantity. One will rotate the plane polarized light towards right while the other will be rotating towards left to the equal angle, and that is why the compound will be optically inactive, and this phenomenon is called as external compensation. The compound become optically inactive just because of the mixing of the enantiomer externally. Now moving to the next, that is retention of configuration. Now what do we mean by retention of configuration? Say for example, if a compound is like this say the compound is like this, 2-chlorobutane. So this is the compound. Now the mirror image of this, now this 2-chlorobutane is undergoing reaction with aqueous NaOH, so it will lead to the product in this way. The product obtained will be like this. So here there is no change in the structure except then that in place of one nucleophile, that is chlorine, the other nucleophile OH has come. So that's how the at the same position also. So this type of phenomenon is called as retention of configuration, where just the groups are changed but there is no change in their position or in their direction. So that is called as retention of configuration. But if the compound is like this, say we have H here and now here you can see that the OH is just in the opposite direction as Cl was present. So this type of compound where the position of any group or atoms is just reversed is called as inversion of configuration, retention of configuration and inversion of configuration. That's all about the terms related with the optical isomers. Thank you.